Section 8.3 was about hypothesis test for population proportions, and section 8.4 is about hypothesis test for the mean. So recall, when the population standard deviation sigmas are known, then the sample mean is distributed as a t-distribution, with a mean of equal to the population mean, and the standard deviation S, the sample standard deviation, by the square root of n. So the sampling distribution of the mean, the sample mean, follows a t-distribution, with degrees of freedom, df, equals n minus 1, with a mean equal to mu, and the standard deviation of S, the sample standard deviation, divided by the square root of n. So if the test statistic for the mean, for the t-score, we compute as follows. If the population is normal, the population is normal, so the test statistic, the t-score for a mean, is if 1, the population is normal or nearly normal and doesn't have any outliers, or, either or, if n is large. N is large. And by that we mean n is greater than or equal to 30. In that case, the t-test statistic is a t-score, and it's defined as the sample mean minus mu sub 0, or nu naught, which comes from the hypothesis, divided by S, the sample standard deviation, by the square root of n, where n is the sample size, with degrees of freedom equal to n minus 1. Let's determine some critical values from a table. Find and draw the critical value for t for a left-tailed test given that alpha is 0.01 and n equals 18. So we know that our degrees of freedom is equal to 18 minus 1, or 17, and alpha is 0.01, so we look at the table. So 17 is right here, and 0.01 is here, and so we have 2.567. 2.567. So minus t sub alpha, since it's on the left, is minus 2.567. So here's our corresponding sketch. Here's our distribution. It's a left-tailed distribution, a left-tailed test, rather. So here's our area of 0.01, that's our alpha, and then the t sub 0.1 is on the left, so it's minus, is minus 2.567. For the next example, we are finding the critical values minus t sub alpha divided by 2 and t sub alpha for a two-tailed test, with alpha being 0.05 and n equals 11. So we know that degrees of freedom is 11 minus 1, or equal to 10. Each area is equal to alpha divided by 2, or 0.025, 0.025. And this are t sub alpha divided by 2, t sub alpha divided by 2, and minus t sub alpha divided by 2. And so t sub alpha divided by 2 is t sub 0.025. And for 10 degrees of freedom, so we go to 10 degrees of freedom, and we go to 0.025, and we find it's equal to 2.228 equals plus or minus, well, plus 2.228, and for the minus value we have minus 2.228. In other words, this point here is minus 2.228, and this point here is 2.228. So let's look at an example. Study time. A university says the mean number of study hours per week for full-time students, that means 12 units or more, should be at least 20 hours. Based on the random sample of weekly study hours for 8 full-time students listed below, is the mean study time for all full-time students less than the recommended amount? And here we're supposed to use an alpha of 0.10. When we check our data for normality requirements and outliers, we find it is somewhat normally distributed and there are no outliers. And so let's go through the 6 steps. There's 5 steps here. Number 1, our null hypothesis would be that the mean number of hours studied is 20. And our alternative hypothesis is mu is less than 20 hours. Next, we need to find our critical values, critical value and rejection region. So this tells us it's a left tail distribution. So critical value. So the critical value for alpha being 0.1, 0.10, if you look for t sub 0.10 for a degree of freedom 7. So here's our degrees of freedom 7, and here's 0.1. So our critical value is 1.415, but because it's a left tail distribution, it's minus 1.415, minus 1.415. So our critical value is minus 1.415. Here's our graph. This is the area, 0.1. And here's our critical t-value. T sub 0.1 is minus 1.415, since it's a left-tailed hypothesis test. From our given value, we determine that the sample mean is equal to 19.175. So that's the sample mean of the given data here. And the sample standard deviation, S, is equal to 2.608 using technology. And then our t-test statistic is equal to the sample mean minus mu divided by S, the sample standard deviation, by the square root of n. So in this case, it would be 19.175 minus 20. That comes from our null hypothesis. 20 minus 20 divided by 2.608, the sample standard deviation, 2.608, divided by the square root of 8, and that turns out to be minus 0.89. So that's our t-test statistic. Using technology, the p-value turns out to be 0.2003. So now we need to decide, is our test statistic of minus 0.89, 895 actually, is that in the rejection region? Well, our rejection region begins at minus 1.415, so minus 0.895 would be right here. So it does not fall in the rejection region, no. The t-test statistic is not in rejection region. And that means we fail to reject H0, the null hypothesis. Fail to reject the null hypothesis. Similarly, when we compare the p-value with alpha, we ask, is the p-value 0.2003 less than alpha or less than 0.10? The answer is no. Again, that's another indication that we failed to reject the null hypothesis. So now we are ready to write our conclusion, which is at the 10% level of significance, this data does not provide significant evidence to conclude that the mean study time for all full-time students is less than the recommended 20 hours per week. So again, here's our conclusion statement. At the 10% significance level, the data does not provide significant evidence to conclude that the mean study time for all full-time students is less than the recommended 20 hours per week. Here's an example about Apple stock. First of all, an explanation. The volume of a stock is the number of shares traded in the stock in a day. The mean volume of Apple stock in 2007 was 35.14 million shares. Now, here's the problem statement. A stock analyst believes that the volume of Apple stock has increased since then. He randomly selects 40 trading days and determines the sample mean volume to be 41.06 million shares with a sample standard deviation of 15.07 million shares. So here's the problem statement in terms of what we're supposed to test. Test the analyst's claim that at the alpha equal 10% level, or 0.1 or 10% level of significance, using p-values and critical values. So first of all, we do a requirement check, and n is certainly greater than or equal to 30. Now, number one, our hypothesis, our null hypothesis, is that the mean equals 35.14, and that's a million of shares. And the alternative hypothesis is that the mean is greater than 35.14 million shares. Now, we know that the the alpha level is equal to 2 alpha level is equal to 10% or 0.10. So here's our critical region. So here's our sketch for the distribution, and our t sub 0.10, the area here is 0.10 because we have an alpha of 0.10. And since n is equal to 40, our degrees of freedom is 39. So we look for degrees of freedom of 39 at 0.10. And so there would be 1.304. 1.304, 39, 10%. So 1.304, so our critical value is 1.304. Number 3 would be our test statistic. And so our test statistic using technology is equal to t equals 2.484. And our p-value, again using technology, the p-value is equal to 0.0087. Now the fifth step is we decide so is t was 2.484 in the rejection region. Well, here's 1.304, so 2.484 would be to the right of it, so it would be in the rejection region. T equal test statistic 2.484 is in the rejection region. Furthermore, our p-value is less than alpha because 0.0087 is less than 0.10. So we reject the null hypothesis on both, for both reasons. Number one, the test statistic is in the rejection region, and p is much smaller than alpha. So we write our conclusion. At the 10% level of significance, this data does provide significant evidence to conclude that the mean volume of apple stock has increased. The next example is about body temperature. Almost everyone identifies the mean body temperature for healthy adults as 98.6 degrees Fahrenheit. The University of Maryland researchers measured the body temperatures of 106 healthy volunteers and found a sample mean of 98.2 degrees with a sample standard deviation of 0.62 degrees. At the alpha level of 0.05 or 5%, can we conclude the currently accepted value of 98.6 is no longer accurate. The initial requirement check that n be greater than or equal to 0 works out. And now for our hypothesis, our null hypothesis is that the mean mu is equal to 98.6 degrees Fahrenheit, and the alternative hypothesis is that the mean is not equal to 98.6 degrees. So we have a two-tiered distribution here. So the number 2, the rejection region, is two-tailed, rejection region. Let's graph that. So here's our graph. Here's 0, of course. And here are two rejection regions of alpha divided by 2 is 0.025. And so here's minus t.025. And here's alpha divided by 2 on the other side. For the right tail, t sub 0.025. And when we look it up on the table for n equals 105, well, we don't really have 105, but it's a little bit over 100, so that turns out to be 1.983. And since it's two-tailed, it is plus or minus. So this is minus 1.983. And this would be the positive of 1.983. Number 3 is our test statistic. Test statistic. And we've got all the information. We've got the mean, we've got the sample standard deviation. And when we do that using technology or doing it manually, we find that our t-test statistic is minus 6.64. Minus 6.64. And the corresponding p-value is 0.00001. So now we need to conclude. So 0.5 would be the decision. We look at the test statistic and we ask, is that in the rejection region? Well, the t-critical value is minus 1.983, so that's here. Minus 6.64, of course, would be way into the rejection region, so that would suggest to reject the null hypothesis. But let's look at the p-value. So is the p-value 0.0001 less than alpha, or 0.05? Yes, it is. So by comparison, so the test statistic is in the rejection region. The p-value is less than alpha, therefore reject the null hypothesis. So now we can write our concluding statement. And that'll be that at the 5% level of significance, that's what alpha was, or is, this data provides strong evidence to conclude that the mean body temperature of healthy adults is different from 98.6 degrees Fahrenheit. Again, here's a concluding statement. At the 5% level of significance, this data provides strong evidence to conclude that the mean body temperature of healthy adults is different than 98.6 degrees Fahrenheit. The next example deals with major engine failure. Here a sampling of 191 buses found that the average time before the first major engine failure was 96,700 miles, with a standard deviation of 37,500 miles. At the alpha level of 0.05, test the manufacturer's claim that the mean distance before major engine failure is more than 90,000 miles. First of all, the requirement check is n greater than or equal to 30. Yes, it is. And now we write our hypotheses. The null hypothesis is that the mean, mu, is equal to 90,000. And the alternative hypothesis, the mean is greater than 90,000 miles. Okay, let's draw the rejection region. And here alpha is equal to 0.5. So here we have our rejection region at t sub 0.05. Here's our rejection region. Alpha is equal to 0.05. And so we have n is 190 degrees of freedom. Our tables don't really go that far, so we use technology. And we find that T sub alpha is 1.653. 1.653. That's our critical value for T sub alpha being 0.05. And then our test statistic, T using technology, is equal to 2.469, and our corresponding p-value, also using technology, is equal to 0.0072. So this is our test statistic. Here's our p-value. And number 5, we now decide as a test statistic in the rejection region. And since this is equal to 1.653, 2.469 is to the right. So yes, in the rejection region, yes. And is p less than alpha? Is 0.0072 less than 0.05? And the answer is also yes. So on both counts, then we reject the null hypothesis. Reject the null hypothesis. So our statement then, in conclusion, is, I won't be able to fit that in, but we can say that at the 5% significance level, this data does provide significant evidence to conclude that the mean distance before major engine failure is more than 90,000 miles. So let me repeat, at the 5% level of significance, this data does provide significant evidence to conclude that the mean distance before major engine failure is more than 90,000 miles. Next is an example from the soft drink industry. And a can of 7-Up states that the contents of the can are 355 milliliters. A quality control engineer is worried that the filling machine is miscalibrated. In other words, she wants to make sure that the machine is not under or overfilling the cans. She randomly selects 9 cans of 7-Up and measures the contents. And she obtains the following data. So here are the amounts in milliliters. So the question is there evidence at the alpha equals 0.05 level to support the quality control engineer's claim? So here the sample size n is less than 30. So when we check for normality, that works out. And with a box whisker plot diagram, we notice no outliers. So we are okay, we can use the procedure that we are used to here. So number one is our null hypothesis, and that is that the mean is equal to 365 milliliters. And our alternative hypothesis says that the mean is not equal to 365 milliliters. And now our rejection region, 2, 1, 2, rejection region, for alpha 0.05, n equals 9, degrees of freedom equals 8. So now we do our graph. So the alternative hypothesis tells us we have a two-tailed distribution. So here's our graph where half the area, or 0.025, is on the left tail and 0.025 is on the right tail. So here's our t sub alpha divided by 2, our critical value, minus t sub alpha divided by 2, and our plus t sub alpha divided by 2. So for 8 degrees of freedom and a confidence level of 0.025 in each one, so 8 degrees of freedom, 0.025, means we add 2.306, so plus or minus 2.306, and here's plus 2.306. These are our critical values. And now when we do our test statistic for t, the test statistic is, using technology, is equal to 1.443, and our p-value, again using technology, is 0.1869. So now when we decide, is the test statistic inside the rejection region, and 1.443 would be about here if 2.306 is here. So a test statistic is not in the rejection region, not in rejection region. And when we compare our p-value of 0.1869, when we look, is 0.1869 less than our alpha level 0.05? And the answer is no. So in other words, we fail to reject the null hypothesis. Fail to reject the null hypothesis. And I won't be able to get my conclusion statement in here, but it reads as follows. At the 5% level of significance, this data does not provide significant evidence to conclude that the mean contents differ from 355 milliliters. In other words, the machine is opposite to 5. I'm sorry. 355. So in other words, the machine is not miscalibrated. Everything is just fine based on the data that we have here. As we had mentioned before, a quick alternative for deciding whether to reject the null hypothesis or fail to reject is in a two-tailed test to compute the confidence interval for mu using the sample data. And if the confidence interval contains mu sub 0, in other words, the mean in the null hypothesis, H0, do not reject the null hypothesis. So that's if the confidence interval contains mu sub 0. If the confidence interval lands away from mu sub 0, the mean in the null hypothesis, H0, then we do reject the null hypothesis. So compute the 95% confidence interval for the mean contents of the 7-up cans using the data above that we just went over. Use the result to test the quality control engineer's claim that the filling machine is miscalibrated. So to compute the t-interval confidence level for mu using the sample data and the null hypothesis that the mean is equal to 355 milliliter and the alternative hypothesis with the mean not being equal to 355 milliliters, it turns out the t-interval, the confidence interval, is from 3.54.0 to 359.3. So that's our confidence interval. And it does include the null hypothesis value of 355. So now, in other words, this says the mu equals 355 is in the interval, So that says do not or fail to reject the null hypothesis. Again, the concluding statement would be, at the 5% level of significance, the data does not contradict the null hypothesis. There is no evidence to conclude that the mean contents of the 7-up can differs from the 355 milliliters on the label. In other words, the machine is not miscalibrated. This concludes section 8.4.